So it's my pleasure to introduce Owen Evans. Owen is Principal Dynamics Engineer in the Dynamics Gauging and Testing team at Atkins Realis in Derby. He joined the railway as sponsored student with Brell in 1985. After gaining experience in the bogie design and structural analysis, took over the Dynamics Works at Adtran's Bogie Division in 1996. He joined AEA Technology Rail as Vehicle Dynamics Consultant in 2001 and moved to S&C Lavenlin, now Atkins Realis in 2022, when Resonate withdrew there from Vehicle Dynamics. That's a quick introduction. And Owen, please do welcome Owen in the usual way.
Toby, it was 2020. I've been here nearly 5 years, which is horrifying. So I can't really read that screen. I can read that one, so I'm going to be mobile. Okay, so you have to be a bit better with your tomatoes. So welcome. Tonight's talk is entitled Vampire Past, Present and Future, which hopefully will whet people's appetites also. Vampire, what is this? So hopefully I can unpack that for you. Yeah, that's me with my other hat on. Can't keep me off a drum kit. Yeah, that's out of date. I'm nearly 40 years on the railway now, which is quite scary, but great fun. Wouldn't have wanted to do anything else. So I play drums. Also, I want to thank two members of our team who prepared many of these original slides. You may know some of them, Fazana Hampshire and Phil Rogers, who's on some of the RSSB committees, and my young colleague Nilesh Sachithanandam, who helped to update the slides as well. So I thought I'd pinch a quote here. Isaac Newton is supposed to have said, "If I have seen the future, it is by standing on the shoulders of giants." So we do quite cool stuff in Vampire these days, but we must never forget the pioneers back in the days of British rail research in the 60s, 70s, 80s, who laid the foundations on which Vampire is built. So dedicate the talk to them. Right, without further ado, let's crack on. So this is the shape of the presentation. So we'll start by asking, what is railway vehicle dynamics? What is Vampire? Where did Vampire originate? Why is it called Vampire? Rubbish. Right. Our role in the Vampire story, Atkins Realis, what you can use Vampire for, and what's happening in the future. There are a few use case slides at the end. We'll see if everybody's still awake and if you want to pursue those when we get there. We can get the main bit done. So, what is railway vehicle dynamics? So, dynamics in general is the study of masses in motion. So, kinematics is the study of motion, but not including the mass. It's just where are things. When you start to include the mass and the inertias and the accelerations of particles or masses moving, that takes you into the realm of dynamics. Vehicle dynamics is a particular subset of that looks at vehicles, all kinds of vehicles. So they can be road, rail vehicles, space, any kind of vehicles. And then to become more specific, railway vehicle dynamics focuses that down specifically onto railway vehicles. Many of the aspects of it are shared across all kinds of vehicle dynamics, but there are some special things about railway vehicle dynamics, the main one being the steel wheel to steel rail interface. Also, the fact that our vehicles don't pitch or yaw very quickly. They don't turn upside down. They generally have quite an ordered passage through the world, which makes some of the maths a little bit easier. But the wheel to rail interface is central to it. So what we do covers modal, frequency and damping. So if you remember things like this, a single degree of freedom system, we've got a mass at the top, we've got a spring and we've got a damper and we've got some input, which is hopefully the track's not quite that bad, but it's giving it some input, and that is being transmitted to the mass through the spring, and the damper is trying to control things and dissipate the energy. So that's a very simple view of what we do in dynamics. And that system will have a frequency, 1/2 pi root k over m, yes? There are other nice equations we can use for simple linear systems. So we can calculate the frequency and the damping. Once we know that, we can look at things like ride quality. Will your coffee spill? Will you be able to sleep on the sleeper? Derailment risk. So we can look at how the wheels interact with the rails. Can the wheels actually climb over the rails? Will the vehicle roll over if it goes around a corner too fast? We have the cyclic top requirement as well. So if a vehicle encounters a repeated vertical fault in the track, will it start to bounce more and more until it jumps off? Some of them do. We could look at rail and wheel wear, gauging. Will vehicles fit through tunnels, bridges, past platforms, that kind of thing? That's a large part of our team's work. So they're the kind of things we look at in dynamics. As you can appreciate, it's complicated. A railway vehicle is a lot more complicated than that. So we need a computer and some software. And here it is. So Vampire is what we call a multi-body simulation package. So it models an engineering system as an assembly of masses connected by suspension elements. So in the simplest analysis, they are linear springs and linear dampers. But we can have bump stops, friction, air springs, shear springs, all kinds of different things that you will find on a railway vehicle. We can model them, stick them in the model. It's based on equations of motion. So the linear analysis with just springs and dampers that have a quoted rate, we can do old-fashioned eigenvalue analysis. We can basically solve lots of equations and characterize those vehicles in terms of frequency and damping. But most vehicles are not like that. They include non-linearities like bump stops that do nothing and then they collide, or friction that does nothing and then it slides. So that's what we call a non-linearity, and you can't really model that with an equation. You have to use a time-stepping algorithm. So we do a simulation typically every millisecond or maybe less than a millisecond, and we see what's happened in the previous millisecond, then we see the forces that are applied to the masses. Then we know how the masses accelerate, so then we integrate twice to find where they've moved to, which then tells you how much all the things connected to them have moved, from which you can then calculate the forces, which then cause the accelerations, and you go round and round the loop very, very fast. So the equations are actually fairly simple, but they're applied very, very quickly. The model includes masses, so things like the car body, bogies, wheel sets, the main big masses in a vehicle. Include their actual mass, their inertia, so that's their resistance to rotation as well as resistance to linear movement, center of gravity positions, and then the things that join them up. We have springs, dampers, anti-roll bars, bump stops, bushes, air springs, traction links, friction elements, you name it, we put them all in. And we can model different conditions. So normally we will model a vehicle in the tear condition, the lightest, when it's empty. We will model laden conditions. So for a passenger vehicle, that might be seats full, and then crush laden when everybody's jammed in. And for wagons, we might look at a range of load conditions because their suspension is quite non-linear. You sometimes have one spring inside another. And the point where the load is sufficient to be just touching the inner spring is often quite a critical one for dynamics. So we can include whatever loads we like. New and worn conditions, so typically we look at new wheel profiles and worn wheel profiles because they affect the dynamics. I know that because the Meridian unit I came down on today was hunting intermittently. I assume the driver knows, he must have had his teeth shaken out. And typically for air springs, we look at inflated and deflated air springs because even though they spend very little of the time deflated, it completely changes the behaviour of the vehicle and does increase the derailment risk. So we have to look at that. This is a typical visualization of a bogie from a Vampire vehicle model. So we've got our wheel sets, we've got some air springs here, yaw dampers at the side to control the stability of the bogie. The axle boxes are held on by these radial arm bushes, and then we've got a lateral damper, some sort of traction arrangement in the middle, an anti-roll bar, primary dampers at the corners. They're the sorts of things that we include in the model. So the sort of things that go into the model, if we've got the model, is measured track irregularity. So we want to know how the vehicle will respond to track inputs. We can get track data from things like the new measurement train, and we can use huge lengths of it if they're available. So sort of London to Newcastle or Edinburgh is fine. We can just make our way along that. And that includes things like the curves, the cant in the curves, but it also includes all the irregularities, so the little lateral and vertical wobbles, changes in gauge as you run along the track. And we can also have a user-defined track input. So if we want to design a curve, just say, I want a 200-metre curve with 150 mil of cant, 45-metre transitions, for example, you can just make one as a text file. Wheel and rail profiles, so we can have design profiles like a P8 or a P12, or we can measure worn profiles using something like Mini-Prof or Calipri. We can take those into Vampire, and the same things with rails. And then we combine the wheels and the rails together to generate what we call contact data. So we start with the wheels at one side and step them slowly across the rails to the other side, and we calculate the rolling radius, the positions of the contact patches, the size and ellipticity of the contact patches to make a big lookup table, which is one of the things that makes Vampire run very, very fast, because once that table is available, you don't have to keep recalculating it. You can just keep going back to it. But we can change the rail profiles as we go along. So things like switches and crossings, check rails, tram rails, we can model all those as well. With the new longitudinal dynamics, we can also include traction and braking forces at wheel sets. So we can speed the train up or slow it down by applying torques to the wheel sets, or external forces. So maybe we've got a trailer vehicle in a unit that's being pulled along, or it brakes itself or whatever. You can apply external longitudinal forces, and you can apply things like wind loading as well. So there's lots of things you can put into the mix that you get out. So pretty much anything you want. Things we often get out are body accelerations. So that would be for ride quality. We can process them according to EN 12299 and predict ride quality index. Displacement, so if we're doing gauging, we can look at how much the body moves and how near it's going to get to line side structures or trains passing on adjacent lines. We can get suspension component forces and displacement. So if we want to know if we're overloading a damper or a bush, or we want to know what forces that element is putting into the vehicle structure, we can work that out. Bogie accelerations and forces, wheel rail forces. So again, things like track shifting forces that are in the railway group standard 2141, we can predict those. And safety against derailment. So things like flange climbing, Y upon Q. This is an example of Y upon Q output. So this is where the nasty dip in the high rail is. And that's where there's a high risk of the leading outer wheel actually climbing the side of the rail and over the top of the rail into derailment and rollover. But there's anything, wear numbers for wheels or rails. And if the output you want is not available, then you can invent it yourself, as I'll explain later. So why would you use Vampire rather than just testing stuff? Certainly the freight industry was asking this question, certainly around things like cyclic top, which is actually extremely hard to test. But you can systematically optimize things. So you can try lots of different damper rates, different spring rates. You can see the effect of changing a mass or whatever it might be. And you can do it quite quickly. So you can cycle through things and get a big lookup table of results very quickly. You can test new and modified designs without the expense of having to build them and find that they weren't very good, which is always a win. Very useful for demonstrating compliance with standards. And hello, of the RSSB, we need to mention this, that suitably validated models that have been compared in simple tests with the behavior of a real vehicle can then be used to do simulations such as a Y upon Q simulation or a cyclic top, which can lead to acceptance of the vehicle through simulation rather than test. Simulation is cheaper, more flexible and easier to control than track testing. Oh yeah, anybody who's tried to book a path, get crew, you name it, for a track test, you don't have to do that. So what you can do is you can decide a big range of possibilities, which 3 or 4 you might want to do on a track test. So you can use it as like a first sift and then maybe optimize what you do on an actual track test. It allows inputs which are impractical or unsafe in real life. So we can actually roll vehicles over. Nobody cares. Nobody gets hurt. It's fine. We can get measures which are difficult or impossible in real life. So something like as you're rolling along the track, you can actually find out the size of the contact patches between the wheels and the rails and where they are, which would be exceedingly difficult to do in real life. And we can use it from the infrastructure or the vehicle side. So we can look at loads going through the track. I know TfL are probably more interested in what happens to the track than what happens to the vehicles. And likewise, clearances to line side structures, that kind of thing. This is my splash screen, for which I'll make no apology. It's one of my holiday snaps when we were testing a tornado. Best day of my life. Anyway, we can use Vampire to develop new components. So there's things like inerters that are coming into prominence at the moment. We're looking at the possibility of modelling those, seeing how they might be adapted for railway use. Hardware in the loop testing, I believe that there's a rig up at Huddersfield University where you can sit in a mock-up of a railway carriage, and then you can drive it using hydraulic actuators with signals that you can get from Vampire. So you just want to have a little look through the signal you're going to try first to make sure there's no unfortunate spikes in it. You're going to break your leg if you play them through the system, but yeah, you can do that. This is something I've done several times working with the Rail Accident Investigation Branch. You can reproduce the conditions leading up to and after a derailment, try and find out what caused it. So you can do a lot of sort of sensitivity studies and say, was it the weight? Was it the springs? Was it this? Was it that caused it? And then come to a reasoned conclusion based on the simulation. And you can use it for all sorts of stuff. So freight, passenger, on-track machines, light rail, different gauges, even steam engines. This has been done. So that's what you can do with it, but where did it come from? Let's look into the murky past of Vampire. So railway vehicle dynamics actually goes back a long way to a gentleman called Stevenson, who you may have come across, who wrote in a paper in 1821 that he'd noticed this behaviour of a coned wheel set, that it would oscillate when run along a track freely. And this is a fundamental principle of railway vehicle dynamics, and it leads to the hunting that I was experiencing this afternoon if you don't control it properly. So people have been writing papers about this and investigating it for a very long time. There's a great body of literature about it. But it was only probably in the 1960s that people started harnessing the new computer technology to try and get more insight into it. And when British Rail Research was formed in 1964 in Derby, this was one of their key objectives, was to try and understand the dynamics of railway vehicles better by the use of computers. I think one thing that was exercising them quite a lot was that pretty much the entire British four-wheel wagon fleet was dynamically unstable at speeds above about 30 miles an hour. And in the days of steam, they very rarely went above 30 miles an hour, so it didn't really matter. But when you put a big diesel on the front of them and you could whip them up to 50 or 60, on several occasions, very nasty things happened. And they wanted to understand more about that. So they started using computers to do it. Initially, I believe, analog computers, which are really cool, and they actually model the system using the electronic analogues of mechanical components, and you can actually put a shock into the system and you can watch the oscillations happening between resistors and capacitors and whatever. Very, very nice and intuitive, and completely overtaken now by digital computers, which are better but kind of less elegant in a way. So, as we've said, the early work was based on linear equations of motion. So these are equations that you can solve, matrices that you can invert, and you can characterize your vehicle in terms of its frequencies and damping levels. And they got a long way with that. And they received a thing called the McRobert Award in 1975. I've looked into this. It's still awarded. It's a very prestigious engineering award. McRobert actually was a lady. I think she was the widow of somebody who left her quite a lot of money, and she decided to use it to encourage engineering innovation, if you like. And so she had a panel of worthies who each year would sift through various entries and award the coveted medal. In 1975, BR Research actually shared it with Westland Helicopters. A bit of trip for you. But they could only get so far. They were based on 2D simulations, so they had a vertical model and a lateral model, but not a model of everything together, rather than what we use now. And also, using the linear theory, they looked into modelling a vehicle going around a curve, but they soon began to realise that the linear theory didn't really cut it, because things like the flange of the wheel comes into contact with the rail, and suddenly the pattern of the forces between the wheels and the rails radically changes. You can generate very large gauge spreading forces, which linear theory wouldn't predict. And also the creepage, creep forces between the wheels and rails can build up, but they will get to the point where the friction is not sufficient and the wheels will start to slide around the curve. And that sort of thing just isn't covered by a linear theory. So they developed a non-linear theory. And while you've got non-linearities in the wheel-rail interface, you may as well include all the others, like bump stops, friction, all the things that we're used to in the models now. So yes, the linear theory is to do with equations. The non-linear theory includes all these non-linearities, and you really need to solve it using a computer, because you, as I mentioned, every millisecond or so as the vehicle runs along the track, you have to recalculate everything. Have we contacted this bump stop? Has the friction broken out? Has the flange contacted the rail? And if so, all the equations change. So by 1977, non-linear curving theory had been developed. As we'll see in a moment, more testing was done. So all the way through, they were building special vehicles and making measurements to test theory and practice, make sure that the software was doing what it should. So from the non-linear curving program, then a non-linear transient program was developed, which is the one we use with the time stepping in it. We have a look at some of the weird and wonderful vehicles that they used to do this validation. Here's an example, Laboratory 1. So you can see it's a Mark 1 coach. I think like one of them at least was a slim one, one of the Hastings units, I think, with the reduced width so that they could allow it to tilt a little bit without hitting things. It had bogies with adjustable suspension and an onboard generator and data collections. I think there's some vents here where the generator is. And it was used on the Blaenau-Festiniog branch. So if anybody's been up there, there are some screeching, literally screeching curves on that line, which was the ideal place to test the non-linear curving theory, because you were into flange contact straight away, and you could work out where that happened on what radius and then simulate it and see if you got the same answer. And apparently in later years, it was used for tests with independently rotating wheels, which changed all the rules about dynamics, because the two wheels on an axle are normally assumed to be fixed together through the axle. But if they're not, and they can rotate at different speeds, then everything changes. This is another weird and wonderful vehicle. HSFV1, high-speed freight vehicle 1. So it's got a linear suspension, so it's coil springs and dampers and kind of traction rods on the ends. But everything was deliciously adjustable, so you could play with it. You could put different springs, different dampers. And that was used, believe it or not, at speeds up to 100 miles an hour to validate the predictions from the Vampire simulations. And we saw it sitting outside the tech centre about 20 years ago and thought, it's not very pretty, but it's so important to the history of railway vehicle dynamics. hope somebody preserves it. And thank goodness they have. So if you go up to the National Railway Museum locomotion at Shildon, you can see HSFV1 and you can go, ah, I know what that is. Here's another weird one. This is called Decapod Lab 25. So you can see it's basically a container wagon, a Freightliner kind of wagon, but it's got an extra wheel set in the middle. So it's got 10 wheels, hence Decapod. In this photo, it also appears to be fitted with cross-braced bogies. I'm not sure that was always the case, but these are quite interesting. They allow the wheel sets to steer in curves independently of the frame of the bogie. Looks like it's a crew. So you'd run along and then you could lower the middle wheel set onto the track, and then you could do weird things like turning it at an angle to the track so it was kind of sliding along slightly sideways, and you could measure the forces on it as that happened. So it's used to verify the nonlinear transient program and study derailment limits. So if you turn this wheel set far enough, it will climb over the rail, and you're just trying to work out how far you had to turn it for that to happen. But of course, the best one of them all was this thing. Probably half your parents don't even remember this, but this is the Advanced Passenger Train E, the experimental one rather than the production one, which was quite a long time in the gestation, but it was an absolute phenomenal achievement when they got it running. I think this is it coming past the gas holders into St Pancras. It was powered by gas turbines, and there is a very significant test run that was done with it in, I think, October 1975, when it got from St Pancras to Leicester in 58 minutes. And you'd be pushing it to do that today in a Meridian, but this thing was on, bear in mind, a timber sleepered, bullhead railed railway with semaphore signalling, which had not seen a fat lot of investment since the days of the Midland Railway in the 1920s. And this kind of spaceship thing arrived and showed what could be done on a conventional railway. And it was also very useful for the development of vehicle dynamics. So it had lightweight aluminium body, articulated bogies, so the adjacent vehicle shared bogies, like the TGV does. It had a tilt system, so the idea was that it could go fast around any given curve, like the Pendolino subsequently does, by tilting. So although it was perhaps curving at 12 degrees cant efficiency, the passengers would only feel 6 degrees cant efficiency, so you could get there quicker. Given that you were going like the clappers and that the signals were not going to be changed because that took money, you had to be able to stop very effectively. So they fitted it with hydrokinetic brakes. So the axles were just great big hollow things with turbines inside them. And when you needed to stop, you pumped oil into the axles, and the turbulence in the oil was then used to generate heat, which was then dissipated through radiators. And my goodness, it stopped so long as the axles didn't break in half, which one did. But very useful for understanding dynamics. And understanding that allowed it to operate up to 250 kilometres per hour on the main lines as they were in the mid-1970s, which is a remarkable achievement. So there's also a wealth of test results that came from all the tests that were done on it, which were plugged back into developing what eventually became Vampire. So, by the 1980s, the various teams at BR Research had developed 4 largely separate programs. So there was the linear eigenvalue program, which is this thing that allows you to characterize the frequency of the bounce and the pitch and the whatever of the vehicle and how much damping is in each mode. The linear response program, which is effectively characterizing the vehicle by a transfer function, and then you can put a linear definition of track irregularity and or force into the transfer function and get a spectral output. So outputs in terms of frequency. Then we got probably next up the nonlinear curving program, which allowed you to simulate what happens as the vehicle goes around the curve with the nonlinearities included, like the flange, friction breakout, bump stops, everything. And that then immediately sort of led to the nonlinear transient program. So we had those 4 programs. but they were all kind of separate. They didn't all use the same vehicle model, and they weren't all accessible from the same front end. So what I decided to do was to bring them all together and change them so that they all use the same model, and that is a full 3D model, a lateral and vertical model combined, and call it Vampire. And that's what they did. What has also been added strangely since is a static program. So it sounds a bit odd having a static program in a dynamics package, but it is actually very useful because we can use it for modeling things like laboratory tests. So if you've seen delta Q upon Q tests or sway tests, we can model that kind of thing. Because the vehicle isn't moving, the modeling of the wheel rail interface can be very much simplified. So they run very, very quickly. So it's quite a useful addition. Anybody remember those? So this was a big step forward, this thing, because originally they used to run it on mainframe computers, which are probably in a completely different town. So you would formulate the questions you wanted to ask the programs in the form of punch cards. I've been told about these. I don't think I've seen them. But yeah, you would generate a deck of punch cards and then you would tie it all together, because if one of them was upside down, it would ruin everything. They all had to be in the right way round and in the right order. And you would take them along to somebody who would put them through a machine, and that would be sent to Birmingham or somewhere, and they would run your eigenvalue analysis overnight. And then you get the answer the next morning and it would say there's 4% damping in the bounce. And you go, right, wanted 5. Another set of punch cards. This analysis will now run in about half a second. So we've moved on a bit, and that was partly due to the emergence of the personal computer, also some workstations and VMS VAX computers. I've actually run Vampire on all 3 of these things. And so as the performance of PCs has gone up and up and up, Vampire has been able to run faster and faster, and we've been able to use unlimited lengths of track, so we can just keep shoveling track in and it will carry on running along it. So if you want to run the whole of the East Coast Main Line, that's fine, we can do that. You can put more detail into the models too. Yeah, this is what you really come to see, isn't it? This is so bad. So originally, they needed a name for it. Somebody said, why not Grandpa? I think we can think, why not Grandpa? The reason for it was that one of the packages that was a predecessor was called the Vehicle Dynamics Modeling Program. Gosh, exciting, VDMP. And somebody sort of looked at that and thought, well, if that was an A instead, and then you put some bits on the end, you could come up with a catchy name that people would remember. They might or might not like it, but they would remember it. Yeah, so what it is supposedly is that, which is terrible, isn't it? No, yeah, don't shoot the messenger, but that is officially, and apparently the logo in the corner of the plots was the front end of an HST, and somebody said, well, that looks a bit limp. I know, and he took the lid off his kettle, put it down on the logo and drew around the lid, and there you go, it's in a circle now, it looks better. And that's how it looked for a long time until we upgraded it to look a bit more like a Space Invader. We prefer this. You pays your money and you takes your choice, really. So, has it been validated? Is this all just nice made-up numbers? Has no connection with reality? Well, we've already said that all through the generation of the Vampire predecessor programs, they were rigorously validated against test results, and BR Research had the muscle to do that. I don't think there's any organisation that could do it now in this country to, build a 10-wheel test vehicle and fit it up with control systems and all that sort of stuff. It's a huge undertaking, but that gives us confidence that it's built on a firm foundation. And then this isn't exactly validation, this is benchmarking, but in 1997-8, Manchester Metropolitan University, the forerunner of the university, well, the Institute of Rail Research at Huddersfield, undertook a benchmarking exercise of 5 big railway dynamics packages: Vampire, New Cars, Adams, Genesis and Simpac. I think since then Adams and Genesis have kind of fallen by the wayside. New Cars is still around. That's an American package. Suspiciously like Vampire in its innards because it was written by two guys from BR Research who pocketed the code and emigrated, but we'll say no more about that. And then Simpac is probably our main rival, and that is a full dynamics package, not just railway dynamics. So it will do all kinds of things that you wouldn't try to do in Vampire. But that makes it a little bit hard to use and terrifically slow by comparison. But the upshot of all this, and this was published in this very worthy special edition of the Journal of Vehicle System Dynamics, originally published in 1998. Everybody submitted their results and they all compared them, and most of them went, "Ooh, crikey, oh, we better do that again." But the Vampire team said, "No, it's fine. Yeah, we'll stand by what we said." And the results turned out very positively. So there was good agreement between Vampire, New Cars and Genesis, which is significant because those three were the railway specific packages rather than the general ones. Probably not a huge lot between Vampire and New Cars. I think the Genesis results were good, but Genesis was very, very slow by comparison with the other two. Yeah, so Vampire and New Cars, but at the time New Cars hadn't done a lot of development to make it more user-friendly. I think it's very capable, but you have to be a bit of an enthusiast to make a model in New Cars. So, bringing the story up to date, what has happened recently. So Vampire was originally developed by BR Research in 1996. As part of the rail privatisation, BR Research was bought by AEA Technology, the technology arm of the Atomic Energy Authority. In 2006, AEA Technology spun off its railway activities as a separate business, which called itself Delta Rail. And that simply renamed itself Resonate in 2016. So it was the same organisation. So there was a fair bit of continuity there. But in 2020, our team had dwindled to 4 members, 2 of whom announced they intended to retire. And as Resonate was really far more interested in signalling and traffic control systems, they gleefully said, "Right, we'll get rid of Vampire then." But there were many voices out there that said, "We'd really rather you didn't." And so, somewhat belatedly, they made a third option available, which is what we call an exploitation license, which would allow a third party to license Vampire to get access to the source code, to update it, support it, and license it to third parties, which is what we needed to allow Vampire to continue. So at that point, SNC Lavalin Atkins acquired one of these exploitation licenses. So they don't actually own Vampire, it's still owned strictly by Resonate, but that is at the level it was when we switched here. But of course, we've now developed it further since then. And it was at this point that I also moved across with Vampire, having followed it from the AA Technology days, because I thought, well, I don't want to do signalling, I'll do Vampire. Can I be made redundant, please? Thank you. So then I went across the road and picked up where I left off. So the first thing that SNC Lavalin did was to rebrand the last version that Resonate had done. So version 7 was not technically different in any way from 6.6, but it was rebranded to put the SNC Lavalin brand on it and to remove references to Vampire as a registered trademark because they wouldn't let us have that. And then we did an enhancement release in May 21, 7.10, and then a bigger release in version 8 in 2022, which added an inline creep law. So instead of doing this pre-calculation of the contact data, if you want, you can calculate it at every time step through the simulation, which allows you to do weird things like rails that roll outwards under the effect of the lateral forces. We are now looking at adding in things like wheel flats actually on the wheels, whereas before we've had to model them by making the rail head profile a weird shape, but we can now start looking at having flat wheels, interesting stuff like that, but it does run a lot slower than the standard version. And when this slide was created, we'd sold 50 licenses to 30 clients in 11 countries all over the place. And we still keep getting new inquiries for it. So it's very much alive and thriving. So what's happening next? So there's a special version 8.11. So for you youngsters in the IMechE, you may be familiar with the Railway Challenge. What we decided to do was to make a cut-down version of Vampire available free to all the teams participating in the Railway Challenge. And so far this year, 18 teams, there's a couple of them have dropped out, but there's probably 11 or 12 at least have taken up the offer of a free version of Vampire. We'll get on to the next bit in a moment, which is the cloud licensing. But the cloud licensing allows us to switch features of the program on and off. So in fact, what they're getting is a full version of Vampire, but with a license that only allows them to use certain bits of it. So it's a full version, but it won't allow a gauge more than about a foot. It won't allow vehicles that weigh more than about a ton. There's a whole load of restrictions that mean you can't use it for general things, but you can do what you like for a locomotive of this kind of size. And we've done an online training module so that all the people that have the licenses can learn how to use it. And then when they go to work for their future employers, they will all tell them to get Vampire. We're not stupid. The next big release is 8.30, which is due very soon, as ever, probably in the next month. So there is an external program called Contact, which is based on the work of a guy called J.J. Kalka, who's a bit of a legend in the world of wheel rail contact, creep and creepage. And he developed this very complex 3D contact modeling program, which we are able to link up to Vampire and co-simulate with it. So that's coming out next. The older elements like the damper, the spring, the bump stop and the friction that had quite a simple position statement have now been refined. That's going through testing at the moment. Certain updates to the graphical user interface. And as I mentioned, a cloud licensing model. So at the moment, if you run Vampire, you need a USB dongle plugged into your machine in order to be able to run it. And customers have been asking whether we could do something a little bit more 21st century. And particularly if you've got somebody that's got two sites 300 miles apart and they only want one license, but you have to get on a train or something and go 300 miles and say, here's the dongle, you can have it until Wednesday and then you need to bring it back. If it's cloud licensing, you can just go on and see if your license is free to use and off you go. And it does open up, as I say, all sorts of options for giving people short licenses or licenses with certain restrictions on them, that kind of thing. So that should be out soon. And what might follow in future? Data plotting improvements. Now this, for those of you who are familiar with Vampire, it has the idiosyncrasy that when you plot results on a graph, you can only have 5 lines on the graph. Who we need to blame for this is lost in the mists of time, but we'd really rather like 8, wouldn't you? You've got 8 wheels, 8 plots. I think putting the plots on the graph is easy, but then you have a legend with 8 things on it, which you have to fit somewhere. So such is the interest in that I think they're going to have a look and see if that can be done. Contact patch plotting. So we know where the contact patches between the wheels and the rails are, and we know how they move and what shape they are. And we have an animator, so we can create an animation of a vehicle running along the track. So kind of combining those things, it should be possible to sort of run along looking down through a wheel set, if you like, at the contact patch and watch it moving across the rail as you go along and watching its shape change. So that should be possible. Include rail roll in the track model. So we need that in the inline contact calculation. So when you apply lateral forces to the rails themselves might actually roll outwards, which means the head of the rail turns, which affects its interaction with the wheel. So that's something that we could add. What else have we got? More elements to improve modeling couplers and buffers. Yeah. So we have some stuff for couplers. Buffers are very, very difficult to do because they sort of slide about and they can actually, in theory, get hooked behind each other, which will be a very complicated thing to try and model. But that's a little challenge for the future. Always got to have something to be doing. So if you want to know more about Vampire, shameless plug, we have a site, vampire.flix.net, which just has some background information, contact details, and then there is a special part of the site for license holders where you can get hold of software release, and we also do stuff like advanced tutorial guides for particularly interesting things like modelling air springs, or our user subroutine that allows you to customise Vampire. And you can email us on vampire@atkinsrealis.com. This is the jolly team. So you might know some of these people. Hallie Porkas, Dan Derbyshire, Dan Firth, Yunshi Zhao, Nilesh Satchivanandam. I think that's Ed Garner. That's Yusuf Mohammed Sally, who's just joined us from Huddersfield. Ian Hills, yours truly. Jimmy Austin, Phil Rogers, Alan Minnis, who's retired, but he's still helping us because he knows all about this, and Stuart Milodowski. So, have you got an appetite for any more? I want to overrun my welcome, but we've got a couple of minutes. I'll skip through these because I can't read the print anyway. So the main headings are vehicle dynamics, which is what we've been talking about. So how vehicles run along the track, whether they ride well, whether they derail, that sort of stuff. Wheel rail interface, so we can look in detail at forces between the wheels and rails, wear, so the energy that's dissipated as the wheels sort of micro slip along the rails that can lead to wear, and also RCF. Gauging, big thing in this country, particularly where we have our Victorian infrastructure and everything's a bit tight. We have to optimize every little bit of the gauge we can use. So we have some quite involved techniques that we use for gauging, which rely very much on the fact that Vampire can do a lot of stuff quickly. And then our team also does testing, and we sometimes do things like the peak counting analysis from the group standard. You can do that on test results as well as simulation results. So people, I only did this yesterday, somebody gave me a set of results to put through the Vampire peak counting. This is looking at derailment risk, so we can calculate Y upon Q against Nadal's limit, so you can work out the limit and then work out whether your wheel set is at risk of climbing over the rail. Yeah, so this is a simulation. I'm not sure if that, oh yeah, we have got a little video. Very dark, isn't it? But that wheel is now heading for the head of the rail. Eventually it might drop onto the outside, and these are the standard test tracks that we use, which are defined. They've now been moved to EN 14363. They used to be in GMRT 2141, but you have a canted curve and you have some nasty dips in the high rail to try and persuade the leading outer wheel of the vehicle to climb over the rail. And this is the sort of output that we get compared with the limit. Oh yeah, nasty, nasty. So cyclic top. So some of you may recall a derailment at Gloucester 2013, when a rear vehicle of a container train jumped off the rails in a situation like this. I was very involved in simulating that in Vampire, and it led to the inclusion of the cyclic top test simulation in the railway group standard. On the same day, another container train derailed at was it on the North London line, Hampstead Way, I think, and that was due to a combination of bad track twist and badly loaded containers. So containers with an offset load, and that led to another change in the group standard. So it all kicked off on the 15th of October 2013, I think. So yeah, what happens here is if you've got repeated vertical faults, then you can start to excite a response in the vehicle, and if there's not enough damping in it, the vehicle can literally jump off the track. And that's what happened at Gloucester. I don't know if that's got a... We have another video, so some marvellous cyclic top there. Bit of luck, this one will actually jump off. Yeah, see, it's getting a bit airborne now. Off she goes. There we go. So much better to do that in Vampire than in the real world. Yeah, trade-off between curving and dynamic stability. So if you want to stop the wheel sets wandering across the track, basically you hold them very tightly to a bogie. So with something like a very stiff radial arm bush. Problem then is that when you try and run the vehicle round a curve, the wheel sets can't align themselves to the curve. They start attacking the high rail and causing a lot of wear. So we have to try and optimize the suspension. Or we can use a clever thing like this, which is called a hull bush. And this has been fitted to quite a few passenger fleets in this country. And what it does is it includes an element of damping. So the system looks like this. So you have a very low stiffness and then a much higher stiffness in series with the damper. So the idea is when you're going around curves and things are happening very slowly, then the damping element just moves freely because the velocity is very low. So that side of the circuit is inactive and all you get is the low stiffness. And then as things start to kick off, if the bogie tries to go unstable, then the velocities get much higher, the damper damps, and then eventually it almost locks up. And then it brings this second spring into play, which significantly increases the stiffness of the bush. So you can see here at low frequency, that's the stiffness. And then as the frequency goes up, way up goes the stiffness. So you get a bush which is the best of both worlds. It allows freedom for curving at low frequency and good fixity to maintain stability at high speed. Rolling contact fatigue. So I won't go into this in huge detail, but this is what we call the whole life rail model, which shows that as the wear number T gamma between the wheel and the rail increases, you get an increasing likelihood of rolling contact fatigue up to a point, and then it begins to drop off again. Because what happens is that as the wear increases, you in fact wear the rail away quicker than the cracks are growing. So there is a sort of sweet spot in the middle, if you like, where the cracks are growing faster than the wear when you have the highest risk of rolling contact fatigue. And we can predict that quite easily in Vampire. Dynamic gauging. So this is something we do a lot of. I won't go into it in huge detail, but basically we generate lookup tables of how a vehicle moves at different speeds, different track qualities, and with different amounts of cant. And then you can generate a big lookup table, and then you can put it into a program like ClearRoute and run that table along a particular route through all the measured structures and work out whether the vehicle is likely to get close to them or hit them or whatever. Generating those tables takes quite a while, so Vampire is quite well suited to it. Yes, anybody been to the Festiniog Railway? Yes, this is obviously a Festiniog Railway gravity train. So this is something I used to test out the original longitudinal dynamics. I thought we'll keep it nice and simple. We won't have a locomotive. We'll just put a whole long train on the slope with some gravity and let it go and see what happens. So this is a 39 wagon gravity slate train. And somebody was able to find me a track data file for the line from, I think it was Tallybull to Harbour Station at Portmaddock. And we ran the thing down there. So, and also put in a little user subroutine. So if the speed got too much, a few of the wagons at the front put the brakes on until the speed got down to something reasonable, and then they take the brakes off again. And then you would see how far across the cob it would run. So that was an amusing demonstration of something that we are trying to develop now for looking at long train dynamics, sort of forces in a long train, and potentially doing stuff like sectional timing. So I'm currently developing a simulation running a container train over Shap, from Lancaster to Carlisle, just to see how long it takes to get there. So all sorts of possibilities. And this is the video I knew we got. So normally our models are just one train. Here, I think these may be connected by a very soft element, but they're behaving fairly independently. So Phil did this. Bosh, there it goes, gives it a good nudge. And then it's coming back for some more because the second one's going to slow down again. A little while to run. Here we go. Gives you another one. There we go. So in this case, you can model something like buffers because you know they're hitting each other directly because the track is straight. That's a nice, easy one. It's when you get buffers on curves that life gets very interesting. So there we go. Oh yeah, and close to my heart. So when the new steam loco Tornado was built in 2008, they largely accepted it on grandfather rights because it was the 50th of a class of 49 that had been fine. Network Rail had a few questions that we needed to answer by doing some testing on the Great Central. And we thought, how do we decide whether the results are acceptable or not? So I came up with the great idea of, well, let's test another engine. So we get another grand day out. So we tested Oliver Cromwell, which had just been accepted back onto the main line. We showed that Tornado was better than Oliver Cromwell, so tick the box. But along the line, we ended up making a vampire model of Tornado and validate it against the recorded test run between Newcastle and York, November 2008, which I was privileged to be on. And then we've used that model to create a model of Prince of Wales, which is the new 282 that they're building in Darlington. So that's the Tornado model. That's the car taxi truck at the back, which is a fiendishly complicated thing I'll tell you about in the pub later. We've now got this, which instead of 462 is a 282, and this is what's now being built. And we have used Vampire to assess it against basically 2141. Some bits it was fine, some bits it was not fine, but better than Tornado, and some bits it was really quite bad, like Y upon Q in reverse, where it just sort of climbed over the rails and went off into the scenery. So you need a risk-based approach then. You say, we will not go around curves like that. So that's a quick flight over what happens with Vampire, where it came from. I hope you found it amusing, and very happy to take the odd question. The energy left for those.
So I think that was really, really interesting presentation. So, would anyone like to take the opportunity to ask questions? Main question.
Yes, sir.
I was recently on a IMechE vehicle dynamics course, and they showed us some videos of, I think it was in the 60s or 70s, and they had a nuclear flask.
Oh, yeah.
And some crash, like physical crash tests.
Mm-hmm.
Is the reason we don't, or like as an industry, don't do that kind of thing anymore is because we have this simulation tool? Is that kind of like supplanted all of that physical crash testing?
No, not necessarily. I think that was partly a public relations exercise just to demonstrate how strong those flasks actually are. It's a bit of a one-off, and I believe we're still using the same kind of flask, so we don't need to test it again. You would not easily be able to simulate that kind of thing in Vampire because the whole thing flew up in the air and rolled over, and it all becomes a little bit difficult to predict what happens. And then there were sort of plastic deformations of colliding bodies and things. It's a whole nother level. The only thing we've done a bit like that was, I don't know if you remember the collision at Great Heck when a Land Rover made its way onto the East Coast main line in the middle of the night, and a East Coast DVT hit it. And we actually did some simulations. I think there's a program called Working Model, and they co-simulated between that and Vampire to try and work out what had happened. But it wasn't just Vampire, it was a co-simulation between the two. It was quite complicated. I think they worked out that the Land Rover had gone under the obstacle deflector on the DVT. It had lifted it up, and the retention straps between the body and the bogie had actually lifted the bogie off the rails because the Land Rover had lifted the body off the rails. But yeah, that's pushing the boundaries a little.
Thank you.
Yes, sir.
What challenges and barriers do you face when trying to perhaps supplement physical testing with digital testing? Or are there any areas in physical testing where you think, I feel like that's the next area for digital testing to progress into.
Okay, so there are basic static vehicle tests that we do. So we weigh the vehicles. So if we're validating a model, then we match it up to the weights. And then there is the delta Q upon Q test, where we twist the vehicle and see how the wheels unload in the laboratory. So often that is done as a test, and then we validate against it. And then there is a bogie rotation test, where you yaw the bogie on a special turntable, X factor, and we can validate that. And then there's a sway, where you tip the vehicle over to one side and the body rolls, and you measure its position with a theodolite, and you can validate against that. That's a sort of minimum that we would really like to do to know that our model is accurate. So any less than that, we're in sort of speculation, because we haven't validated the model. Once you've validated the model, then you can use it for other things. Ideally, we would validate against a ride test as well. So you can look at the main frequencies, the bounce frequency, the pitch frequency, that sort of thing, match those. And then you can use your model to predict anything you like, because you're fairly confident that it behaves the same as the real thing. So then you can do, I don't know, add passengers to it. You can deflate the air springs. You can run on rougher track or different track to what was used in the ride test, that kind of thing. That's kind of the limit to the dynamic testing that we normally do. So it will be weighing, delta Q on Q, X factor, sway, and ride. Not a lot more that we would do. And of course, if you're designing a new vehicle, then you can't validate the model, because the vehicle doesn't exist. So you just work with the best parameters you've got. And you may say, okay, well, we think this is this stiffness, but there's a tolerance on it. So we look at different tolerance bands and make sure it will meet the requirements. But I think in terms of getting vehicles into traffic, there will never be a complete elimination of physical testing, because we need to validate the model. But the model can then allow you to test all sorts of other conditions that you haven't been able to test. So I don't know if that answers the question for you. Barry.
Hello. You knowing who you are and what you know and your experience right here, right now, a genie appears and snaps his fingers, saying, I can transport you to any time, to day zero of BR research or the AEA, Resonate days or whichever, with the ability to influence, to change or improve a thing to Vampire. What is there something which is on the forefront of your mind to say, you know what, I wish we did this back in 1997?
Amazing question. The one thing that might spring to mind is that the origins of Vampire are quite informal, I would say. So there were lots of boffins doing amazing things at the Railway Technical Centre, and they were writing bits of code, generally in Fortran, to help them solve their problems. But they were all working independently, and they were writing stuff. I don't think they bothered to document what they wrote particularly well. They just wrote it and it worked. Bosh, done. So reeling back from where we are now, it might have been better if it had been a little bit more joined up at the beginning, and if they'd actually written down what they did, because we now have to dig into the Fortran and work out what they did. And particularly with the handover from AA technology from, Resonate and Alan Minnis, who has so much of this in his head, to a new group, including Ian Hills, who's incredibly clever, but he still needs Alan to tell him some of what's going on in the code. And I think we have now retrospectively gone through and documented a lot of it. There were other horrors, like because computer memory was quite limited back then, they would do stuff like reusing variable names to save memory space. Can you imagine the fun they had on scrambling that? You've got about 1 million lines of Fortran to go through to work out where this CMAX thing has been used and how many different meanings it had, and which ones go with which ones, and then unscrambling it all. So I think we are now in a better place, but I do occasionally talk about it being like the arches underneath Waterloo Station, that they were built a very long time ago. Nobody knows who by, nobody has any drawings. All we know is that they are holding Waterloo Station up, and it's fine. Okay.
Thank you.
I hope that doesn't undermine your confidence in our world-leading software, but everything has a heritage, doesn't it? It does work, but yeah, we've had to put some effort into working out how it works.
Go on, do you have a question?
Yeah, I do. More of a specific question. Vampire seems to be very versatile too. You can model different application, different rail vehicle.
Yeah.
Have you ever had to model road railers?
Model
Road railers.
road railers.
Yes. Quite. They don't have a bogie. They have a
No.
rail gear in a sense. And
Now, one of
quite
our
hybrid.
customers in the States has actually modelled what they call a high rail.
Okay.
And they wouldn't tell us how they'd done it, but they had to model the interface between a pneumatic rubber tyre and a railway rail using Vampire, which they somehow did. And they also came up with a really cool shape file. So when they did their animation, they'd imported something from CAD and they had kind of a chrome grille and wraparound windscreen on this and everything. So yes, it can be done. But the main challenge, I would say, is the modelling of the rubber tyre to rail interface. If that is important, it may not be that important, depending on what you want to know about your high rail. And you would certainly model the little guiding railway wheels, which might be of more interest. So yes, kind of, somebody's done it, but we're not quite sure how.
Yeah, there's a friction drive, I think. Yeah, driven. Is it higher?
Yes.
It's in concept with the rail wheel, right?
Yeah.
Which drive this. So there's a friction drive. There's a still hydrostatic drive, which have rail motors, hydraulically driven rail motors. So that would be a bit different.
Yeah.
You have 4 contact points, so you can model that.
Yes, for some of them, they're just the railway wheels only guide, don't they? And the road wheels are still providing the traction and braking.
That's right.
Yeah.
It could be done, yeah.
Yeah, that could be done. Yeah. It's just a matter of modelling this
Yeah, accurately.
rubber interface. But we have the ability to have a custom user creep law to define the sort of relationship between the creep force and the creepage between the wheel and the rail. So I guess that's how you would try and do it.
I don't think there's any questions on. Well, there is one question online about the recording, which will. Yes, we have recorded it, and we'll share that after.
Nice.
If we do one more in the room.
That's a good one. I guess nowadays, since I guess earlier on, the computer processing is a lot more powerful. So, like, how important do you think it still is that you say like Vampire's quicker? Like, could other software now like sort of compensate just with computers being better?
Well, I think we all compensate by computers being better. So if we were quicker, we're still quicker. It's just they might be catching up to where we used to be, but we're still ahead. So, for example, I ran this container train I mentioned. So it was a Class 66 loco and 10 container wagons, which I ran from Lancaster to Carlisle. And even that model, which is quite a big model, ran quicker than real time. So the real train would have taken, I don't know, an hour and 20, and this ran in about an hour and 5 or something. So there comes a level of complexity in the model where it's about even time. The simulation takes as long as the real run would have taken. And then if I get given some more bits in Vampire, I can make a full 47 wagon train, which is what I need to do to benchmark it against a program called RailSys that we also have in Atkins Realis. And that is going to take a while to run. But if you were to try and run the same thing in Simpac, it probably takes several days, I should think. So yeah, the increase in speed is benefiting all of us. So we're staying ahead.
Great. Well, Owen, thank you very much for coming to talk to us today. You've taken us on a real journey from understanding some of the basics of vehicle dynamics through to some of the fascinating history of how Vampire was developed out of all that great stuff at VR Research through to advanced passenger trains. That was a really fascinating insight. It's good to know that we've had some validation along the way. It's good to see that Vampire is sort of staying at the cutting edge, the leader in this area. I think everyone should have taken something away from that really interesting talk. So can we thank Owen? I'm going to stop recording. Right. So